Okay, now I will talk about the section 7.2, Differential Kinematics. Okay, you know for the case of the open chain, the Jacobian is obtained by using the relationship between the input joint velocity and the twist of end effector. Okay, this is called as Pod kinematics Jacobian. Okay, but in the case of the closed chain, this procedure is a little bit difficult because not all joint actuated. It means the parallel mechanism or closed chain mechanism has the passive joint. Passive joint make the Pod kinematic problem to be difficult. Okay, in many cases, only actuated joint can be described input velocity. In many cases, actuator has the sensor, so we can obtain the sensor information from the actuated joint, not passive joint. So we just know that the active joint angle or active joint displacement, not for the passive joint. But in order to solve the Pod kinematics of the parallel mechanism, we should know the passive joint information. That's the problem of closed chain. Okay, the velocity of a remaining passive joint must then be determined from the kinematic constraint equation. In the case of the differential kinematics, it will be called as constraint Jacobian. Okay, this passive joint velocity are usually required to determine the twist of the closed chain and effector frame. Okay, it means for the kinematics of the closed chain, we should know the passive joint information. For open loop chain, the Pod kinematics Jacobian is central, plays a core role to determine the velocity and static analysis. On the other hand, for the closed chain, the Pod kinematics as well as constraint Jacobian should be determined in advance because they play a central role in the velocity and the static analysis. So in the case of the parallel mechanism, we should know two Jacobian. Okay, let's take the suit golf platform. We have dealt with it in previous lecture. This one, Stewart platform. I will review the structure of the Stewart platform. We will attach the fixed frame here and body frame here on the moving platform. Okay. As you know, this constant vector will be used to determine the kinematics, and then d vector and the p vector plus b both are same each other, so we can determine the di vector, and then we can calculate the length of the leg si here, okay, using the scale operation. Okay, in the previous slide, ik for the Stewart platform obtained easily. Okay, for given body frame orientation r and the position p, okay, as mentioned before, both will provide 6 independent information. Okay, for given r and p, the leg length s can be obtained analytically in the functional form like this. We can write down these equations 6 times according to the order or sequence of the I from 1 through 6. By collecting the 6 equation as a vector, then we can write down the nonlinear vector G, okay, as a 6 dimension. Okay, the G vector G column vector can be differentiated with respect to time, then we can get this inverse Jacobian. Yeah, maybe the round G, round what in here? Maybe R and P. Okay, and then round R and P. Maybe this is the homogeneous transform, and round T. So it will be the twist in here. Okay, so this is the Jacobian. Okay, but this kind of procedure will be very difficult. So it will require considerable algebraic manipulation. Okay, so it's not recommended by this textbook. Okay, it has the many issue to calculate the Jacobian matrix. Okay, as a different approach, I will use a textbook use the conservation of power principle. It will provide Jacobian, inverse Jacobian as a screw axis. Okay. The conservation of power principle is used to determine the static relationship. Maybe you know the tau is equal to J transpose length for the open chain. Okay. This concept will be applied to the parallel mechanism. Okay. Okay. Here, let's assume that the parallel mechanism does not have any external length. It means only the linear poles of a prismatic joint is applied. So, okay, this is the moving platform, the fixed platform here. The leg, if you don't have any external length, you can apply only the linear poles. Linear poles will be denoted by the F. Okay, so Fi is the three-dimensional linear poles. If you know this direction vector and head, maybe the tau will denote the magnitude of the linear poles. Okay, so the F vector using the unit vector and magnitude. Okay, so we will define the F along with the direction of a prismatic joint. Okay, we know this is the space frame or fixed frame. Okay, from in terms of the space frame, we can determine the moment. Okay, for given linear poles, any vector can be chosen to determine the moment. Okay, here, the moment will be the R cross F. The easy way to determine the moment, the A vector can be chosen. Okay, we know the A. Okay, so A cross Fi will be used to denote the moment. Okay, so by collecting the Fn moment, let's collect to write down the length, six-dimensional length. Okay, like this. Okay, so as you know, this straight platform has the 6 leg. Okay. Okay, so the 6 length can be added to determine the resultant length. So we will add everything. Okay. So first linear poles through the last moment and last poles. Okay. In the previous slide, the linear poles will be denoted by the unit vector times magnitude. Okay, this concept will be applied to here. So the linear poles, the Fi is replaced with the n tau. Okay, every column vector has the magnitude of the tau. So this scalar value can be can go outside. Okay, like this, tau 1 and tau 2 and the tau 3. I'm sorry, this is tau 4. Okay, through the tau 6. Okay, let's collect the tau vector from tau 1 through tau 6. At that time, this one will be the first column vector of the any matrix, second column and the third column through sixth column. So we can determine the 6 by 6 matrix. Okay, the definition of the conservation of conservation of power principle. Okay, the tau is equal to J transpose length. So the length will be denoted by the J inverse transpose tau. So this 6 by 6 matrix is equal to J's inverse transpose tau. Okay. So the Pole Jacobian, the special Jacobian of the pole kinematics, and each inverse can be obtained using this definition. So J's inverse will be the given matrix transpose. Okay, you know the in the case of the cross product, if you exchange the vector each other, then minus sign is required, is right? The direction is converted into the opposite direction. So if you change each other, then minus AI is required. Okay, it represents the screw of the first leg. This is the screw of the last leg, sixth leg. So by collecting the screw, we can determine the inverse Jacobian. It makes the pole kinematic issue as an easy one using the inverse. Okay. After collecting the every screw of the leg, if you take the inverse operation, then we can determine the space Jacobian of the pole kinematics. Okay, let's extend this concept to the general parallel mechanism. Okay, till now, the screw or platform, the inverse Jacobian, the inverse matrix of the space Jacobian of the pole kinematics, it is written as a short form inverse Jacobian. Okay, so JS inverse, okay, can be derived in terms of the screw. Those are main concept of this textbook. The screws will be used to denote the inverse Jacobian. What screw is used? Okay, each leg, straight line leg is used to denote the screw of the parallel mechanism. Okay, this concept will be extended to the more general case. Okay, more general parallel mechanism is considered here. Also, we want to apply the static analysis using the conservation of power principle, but it's not straightforward. Less straightforward. So we cannot apply this kind of concept to the parallel mechanism. So we will introduce another concept to solve the pole kinematics of parallel mechanism. Okay. In order to determine the pole kinematic Jacobian, we will take the previous example. Okay. This example has the three legs. The first leg has the M joint. In here, one or two joints will be activated. Other ones will be the passive. The leg 2 has the N joint. Leg 3 has the P joint. Okay, let's take the N and P as of 5. Do you remember the degree of freedom of this mechanism? Okay, the N plus M plus m plus p minus 12. It is equal to the degree of freedom of this mechanism, okay? So if you take the S of 5 for the joint, we will have 3 degree of freedom. Okay, we will consider this concept. So let's assume that the first joint will be activated of the 3 leg. The other joint will be the passive. We don't know the joint angle information of the passive joint. So the passive joint angle or velocity will be determined from the active joint. Okay? It will make the problem difficult. Okay, we have the 3 legs, so we can apply the POE to each leg. The first POE and the second POE and the third POE. From here, we will determine the 2 matrix equation. Okay, first one and the second one. So we have 2 matrix loop constraint. First one and second one. Okay, let's take the time derivative both sides. Then we can get this equation. Maybe you know this one. This will be equal to matrix form of the twist. Is it right? This is the matrix form of second twist, but both twists are same each other because we have the only one end effector frame, body frame. Okay, so this is equal to J1 theta dot. How about the right one? The right side will be equal to J2 pi dot. So from the same twist, we can get the 2 equation using the Jacobian. Okay, here if we move to left hand side, this will be the 0. If we move to the right side, this will be the 0. So by collecting the both sides, we have big matrix and 15-dimensional velocity vector. Okay. Maybe this matrix is very big because the number of row will be the 12. Number of the column will be the 15. Okay, because we have the 15 variable. In the 15 variables, only 3 variables will be activated using the electric motor or some actuators. Okay. By collecting the active joint, we have assumed that every active joint will be chosen as a first one, like this. This is the active joint. Okay. The remaining one, theta 2 dot through theta 5 dot, pi 2 dot through pi 5 dot. Okay, like this, we can collect active joint and the passive joint. So, in here, theta 1 dot, pi 1 dot, psi dot will be collected to denote the active joint vector in R3. Okay, the remaining 12 element will be the passive, so we will denote as a QP. Okay, by collecting active and the passive, this will be the 15-dimensional vector. Okay, in the previous slide, J1 minus J2 and 0 matrix, 0 minus J2, J3 matrix, and theta 1 dot through theta 5 dot, pi 1 dot through 5 dot, psi 1 dot through psi 5 dot. Okay, here let's choose first active joint, theta 1 dot. At that time, the first column vector can be chosen. Okay, and then the 6 pi 1 dot will be the 6th column vector. Is it right? the sixth column vector will be multiplied to the pi 1 dot, and then psi 1 dot will be multiplied to the 11th column vector. By collecting the first 6th, 11th column vector can be collected to the HA. Okay? So HA will belong to R12 times 3. Okay? Because it has the 3 column vectors. Okay, remaining column vectors will be collected to the HP. It belongs to our 12 times 12. Okay, maybe the first column of the HP will be the second one. Okay, like this we can separate QA, active joint, and passive joint by exchanging the column vectors. Okay, so let's denote this equation like this. In here, the QP can be calculated using the inverse of the HP because HP has the square matrix. So we can obtain the velocity of a passive joint using this equation. Okay. In the case of the invertible HP, we can easily determine the velocity of the passive joint. If you know the passive joint angle or passive joint velocity, in here we can collect the theta 2 dot through theta 5 dot. We know that the theta 1 dot from the active joint. So by collecting the fifth element, we can write down this post leg twist. Okay, in here we know that the first column vector of this equation can be chosen from this one. So maybe the 0, 0, 1 vector will be chosen to obtain the theta 1 dot. Okay, and then the theta 2 dot should be obtained from this element. Is it right? So from this equation, the first row vector will be multiplied to the active joint. So first row will be chosen to denote the theta 2 dot, okay, from the active joint. From here, the third joint, theta 3 dot can be chosen from this second row of this matrix. So it can be denoted by the G3, G4, and G5. So the G2, G3 through G5, this matrix will be multiplied to the QA, okay? Because from this one, through the last element, we can write down this twist, okay? So J1 times theta dot as a fifth dimensional vector, okay, theta 1 through theta 5. This theta dot can be chosen using the QA. The first element is the QA dot. Maybe this one is the 0, 0, 1, okay? And the second one through the fifth one is obtained from the QP minus HP inverse HA. I'm not sure the notation of active joint, active Jacobian, the QA dot. So from this matrix, we can chosen we can choose the theta 2 dot through theta 5 dot. It will be applied to here and here and here and here. So by extending the theta dot using the active joint, okay, then the active joint Jacobian will be obtained by multiplying two matrices. Okay. So these two matrix multiplication can be replaced with the JA. Okay, let's summarize. The end-effector twist can be denoted by the theta 1, J1, theta dot. Here, theta dot is obtained using some element from big Jacobian. Here, E1 transpose through G5 transpose. Okay, it will be obtained from the active joint. It is applied to here. So the twist of end effector can be represented as a Jacobian from the active joint. Okay, JA is obtained from like this. This kind of a concept can be applied to the second joint, second leg, and third leg. So we have three equations. So this equation can also have been derived using the either chain 2 and the chain 3, leg 2 and leg 3. Okay, for given value of the active joint QA can be measured using the sensor attached to the actuator. We still need to solve the passive joint. Okay, we should solve the passive joint angle or velocity from the loop constraint equation, this equation. Okay. In many cases, HP lose the length. So, if the HP lose the length, it will be corresponding to the singular configuration. Those kind of singular configuration is called as actuator singularity. Because if you replace or exchange the active joint element, such as the theta 1, from the theta 1 to the theta 5, then the HP matrix will be changed. So actuator singularity is dependent on the actuator location.